Let us begin by quieting the mind. Let us step away from the noise of the day, the rush of the hours, and the bright, demanding lights of our immediate world. Instead, let us drift upward and outward. Imagine rising above the atmosphere, leaving the blue haze of Earth behind and entering the profound velvet silence of deep space. Here, the sun is a piercing white star, and the shadows are absolute. It is a place of stillness, but also a place of ancient, traveling light. In this cold expanse, 1,000,000 miles away from the planet that built it, floats a machine. It is a collection of gold hexagons, a fragile origami of beryllium and plastic, shielding itself from the warmth of the sun. This is the James Webb Space Telescope. It is the most powerful eye we have ever opened to the universe. For months, it coasted through the dark, unfolding its layers like a flower blooming in a vacuum. It cooled itself down to temperatures near absolute zero, shivering off the heat of its own creation so that it could sense the faintest, oldest warmth in the cosmos. It was built to look back. It was built to peer through the curtains of dust and gas that hide the origins of everything we know. The mission was simple, or so we thought. We wanted to see the dawn. We wanted to look back to the very beginning of time, to the moment just after the Big Bang, when the first lights turned on. We have a story about how our universe began. It is a story we have written over decades, piecing together clues from microwave background radiation and the movement of galaxies. We call it the standard model of cosmology. In this story, the early universe was a chaotic, hot soup of particles. As it expanded and cooled, it fell into a dark age, a time before stars, before galaxies, before structure. Slowly, over hundreds of millions of years, gravity began to pull wisps of gas together. The story tells us that the first galaxies should be small, messy, and dim. They should be irregular blobs, the infants of the cosmos, struggling to form amidst the turbulence of a young universe. We expected to see chaos. We expected to see the slow, clumsy assembly of the first structures. We built the James Webb Telescope to confirm this story. We sent it out into the night to take a picture of the baby universe, expecting to see it crawling before it could walk. But when the great golden eye finally opened and the first data began to stream back across the void to Earth, the story did not match the picture. The telescope peered into a patch of sky that looked empty to our eyes. It stared at that nothingness for hours, drinking in the infrared light that had been traveling for 13 billion years. When the image was processed, the screen was not filled with faint, messy smudges of infant galaxies. Instead, it was filled with jewels. Bright, distinct, massive structures. They were not struggling to form. They were already there. They were already grand. This is the beginning of the mystery. This is the moment the silence of the cosmos spoke back to us in a language we did not expect. We went looking for the chaotic beginning, and instead we found a pattern of maturity, of size, and of brightness that should not exist. Imagine walking into a nursery, expecting to find newborns, but instead finding fully grown adults, standing tall, speaking complex languages, and building cities. That is the scale of the anomaly. The universe, in its deepest infancy, appears to be far older than time itself should allow. As we drift here, looking at the golden mirrors of the telescope reflecting the starlight, we must understand the sheer magnitude of what this means. Light takes time to travel. When we look at the moon, we see it as it was 1 second ago. When we look at the sun, we see it as it was 8 minutes ago. When we look at the nearest star, we are looking 4 years into the past. The James Webb Telescope looks back billions of years. It is a time machine. It captures light that left its source when the Earth did not exist, when the sun was not yet born, when the Milky Way itself was perhaps just a vapor. The further we look, the further back in time we go. We are looking for the epoch called cosmic dawn. The light from that time has been stretched by the expansion of the universe. It has shifted from visible light into the infrared. Our eyes cannot see it, but Webb can. Webb feels this ancient heat, and in that heat it detected something that made astrophysicists fall silent. It wasn't just one galaxy, it was many. It was a population. In the very first deep fields, amidst the glittering array of background stars and spiraling nebulas, there were red dots. To the untrained eye, they were insignificant specks, but to those who know the language of light, those red dots were screaming. They were too red, they were too bright. In cosmology, redshift is how we measure distance and time. The redder the object, the faster it is moving away from us, and thus, the further back in time it is. These objects had redshifts that placed them at the very edge of the observable universe, less than 500 million years after the Big Bang. According to everything we know, the universe at that age should have been a place of small, blue, erratic clumps of stars. There simply hadn't been enough time for gravity to pull together enough matter to create something massive. Gravity is a weak force. It works slowly. It takes eons to build a galaxy like our own Milky Way. And yet, there they were. The data suggested these galaxies were as massive as the Milky Way, but existing at a time when the universe was only a fraction of its current age. It was a mathematical impossibility under our current models. It was as if someone had snapped their fingers and created fully formed galaxies out of nothing, skipping billions of years of evolution. The telescope floated on, indifferent to the confusion it had caused. It merely collected the photons, counting them one by one. But on Earth, the confusion turned into a deep, pervasive question. If the universe made these giant structures so quickly, then our understanding of gravity, of dark matter, or of the Big Bang itself might be flawed. The silence of deep space is deceptive. It looks static, but it is alive with information. And the pattern emerging from the deep fields was not random. It wasn't a fluke. Everywhere the telescope looked, it found them. It found these impossible breakers of cosmic law. We call them the universe breakers. But perhaps they are not breaking the universe. Perhaps they are simply breaking our idea of it. Let us float here for a moment longer, contemplating the golden mirrors. They are pointing at a darkness that is not dark. They are revealing a history that is not the one we wrote down in our textbooks. The pattern suggests that the universe woke up early. It suggests that structure and order are not the result of a slow, grinding crawl out of chaos, but perhaps a fundamental, rapid inevitability. The light washing over the telescope is a messenger. It carries a secret. And as we peel back the layers of this light, we find that the mystery deepens. It is not just about the size of these galaxies, it is about their shape. It is about their chemistry. It is about the very rhythm of creation. We are drifting through a cosmos that is stranger than we imagined. We are realizing that the darkness is not empty, and the silence is not quiet. It is humming with a pattern we are only just beginning to hear. To understand the pattern, we must understand the timeline. Visualize the history of the universe as a long, flowing river. At the source there is the Big Bang, a moment of infinite energy and density. The river bursts forth hot and turbulent. For the first few 100,000 years, the water is opaque, a fog of glowing plasma. Then, as the river widens and cools, the fog clears. This is the release of the cosmic microwave background, the afterglow of creation. For a long time, the river flows through the dark. This is the era we call the Dark Ages. There are no stars to light the water. It is a silent, black flow of hydrogen and helium gas. In our standard model, this section of the river is calm. Gravity is the only current, gently nudging the gas into denser and denser currents. Slowly, gradually, the first eddies form. These are the first stars. They are huge, volatile, and short-lived. They ignite, burn furiously, and die. These are the sparks in the dark. As the river continues to flow, these sparks gather together. They form small, irregular rafts, the first dwarf galaxies. These rafts collide, merge, and grow. Over billions of years, the river becomes populated with great ships, the spiral and elliptical galaxies we see today. This is the timeline of gradualism. It is a timeline of slow accumulation. Small things become big things. Simple things become complex things. It is a logical, comfortable progression. But the James Webb Telescope has flown upriver. It has traveled back against the current, past the era of the great ships, past the era of the merging rafts, aiming for that quiet stretch just after the Dark Ages. And there, where we expected to see only the smallest, faintest eddies, we found leviathans. Let us look closely at one of these anomalies. There is a galaxy identified in the data, a smear of red light known as JADES, GSZ14 Neuro. The name is technical, dry, robotic, but the object itself is a marvel. It exists at a time when the universe was less than 300 million years old. In the timeline of the river, this is mere moments after the fog cleared. If our understanding of the universe is correct, a galaxy at this time should be a tiny cluster of stars, barely held together. It should be low in heavy elements, mostly hydrogen and helium. It should be dim. But JADES GSZ14 is bright. It is shockingly luminous. Its light is not the weak flicker of a dying candle, it is the roaring blaze of a bonfire. This brightness tells us two things, and both of them are unsettling. First, it tells us that there are a lot of stars there. Hundreds of millions, perhaps billions of stars. To form that many stars in such a short window of time requires a rate of production that defies our physics. It would mean that gas was collapsing into stars at 100% efficiency, wasting nothing, moving faster than the speed at which gas can naturally cool and condense. It is like baking a 1,000-tier wedding cake in the blink of an eye. Second, the light tells us about the composition of those stars. When we analyze the spectrum of this light, breaking it down into its colors like a rainbow, we see the fingerprints of elements heavier than helium. We see carbon, we see oxygen. This should not be. In the cosmic kitchen, the only elements created by the Big Bang were hydrogen, helium, and a tiny dash of lithium. Every other element, the carbon in your cells, the oxygen in your lungs, the iron in your blood, was forged inside the hearts of stars. Stars have to live, burn their fuel, fuse atoms together, and then explode to scatter these heavy elements into the universe. This takes time. It takes generations of stars living and dying to enrich the cosmos with dust. Finding significant amounts of dust and heavy elements in a galaxy this early is like finding a leather-bound book in a room where paper hasn't been invented yet. It implies that generations of stars had already lived and died, all within a window of time that barely allows for a single generation to exist. The pattern begins to crystallize. It is a pattern of too much, too soon. Too much mass, too much brightness, too much complexity. And it is not just one galaxy. As Webb continued its survey, looking at different patches of the sky, the COSMOS field, the UDS field, the Good South field, the same anomaly appeared. Massive red disk galaxies, spiral arms that were already formed, structures that looked relaxed and settled, as if they had been evolving for billions of years, yet they were sitting at the dawn of time. This forces us to ask a profound question. Did the universe start with a template? In our standard model, structure grows bottom up. Small clumps merge to make big clumps. But what if that is wrong? What if the universe started top down? What if, in the very first moments of the expansion, there were massive fluctuations, huge seeds of gravity that allowed entire galaxies to collapse into existence almost instantly? The pattern detected by Webb hints at something hidden in the dark matter. Dark matter is the invisible scaffolding of the universe. We cannot see it, but we know it is there because of its gravity. We believe that for every visible star there is a halo of dark matter holding it in place. Standard theory says that dark matter halos started small and grew. But the pattern no one can explain suggests that perhaps the dark matter halos were born huge. Perhaps the early universe was not smooth, but wrinkled, rugged terrain of high peaks and deep valleys in the fabric of space-time itself. If this is true, then the very first epoch of the universe was not a slow awakening, but a violent, sudden explosion of creation. It would mean that the dark ages were not dark at all, but filled with the light of monster galaxies burning furiously in the void. Consider the implications for our own existence. We live in a quiet, mature galaxy. We assume that for life to exist, for intelligence to rise, the universe had to go through a long, slow maturation. We assume we are the product of billions of years of stability. But if massive, complex galaxies existed right at the start, could life have started then too? If there were planets circling those ancient stars, enriched with oxygen and carbon far earlier than we thought possible, could the universe have been habitable when it was still a toddler? The pattern Webb has found is not just a problem for equations. It is a rewriting of our cosmic biography. It suggests that the universe is far more efficient at creating order than we gave it credit for. It suggests a drive toward complexity that is woven into the very laws of physics, a drive that acts faster and harder than our conservative models predicted. As we stare at these images, these beautiful, impossible rubies scattered across the black velvet, we feel a shift in our perspective. We used to think of the early universe as a simple place, a place of raw materials waiting to be assembled. Now, we see it as a place of immediate richness. The telescope hangs in the silence, its job far from over. It has shown us the pattern, but it has not yet given us the cause. Is it a flaw in our understanding of gravity? Is it a new force of nature we haven't discovered? Or is it something even stranger, a misunderstanding of the age of the universe itself? Some astronomers have begun to whisper that perhaps the universe is older than 8 billion years. Perhaps the timeline is longer, stretching back into a past we haven't accounted for, giving these galaxies the time they need to grow. It is a radical thought. It challenges the Big Bang itself. But when you are faced with a pattern that defies explanation, you must be willing to question the foundation. We are floating in the unknown. The map we drew is wrong. The river of time has currents we did not see. And as we prepare to dive deeper, to look at the specific physics of these ancient giants, we must hold on to that sense of wonder. We're not just observing data points. We are witnessing the collapse of an old story and the slow, mysterious writing of a new one. The pattern is there, pulsing in the infrared, a heartbeat of the early cosmos that is strong, steady, and inexplicably mature. The silence is broken. The mystery has begun. We return to the deep field. We return to the silence. Let us drift back to those red points of light that the James Webb Telescope has found in the abyss. We have spoken of them as galaxies, as islands of stars spinning in the dark. But there is something else hidden within that light. There is a shadow at the center of the jewel. To understand a pattern that no one can explain, we must look at what lies at the heart of these ancient structures. We must look at the darkness that anchors the light. In the center of almost every massive galaxy we know, including our own Milky Way, there sits a monster, a supermassive black hole. These are objects of such immense density that they puncture the fabric of space. Their gravity is a trap from which nothing, not even light, can escape. For decades, we have believed that these monsters grow slowly. We believed they started as seeds, perhaps the remnants of the very first stars collapsing. A star dies, it leaves behind a black hole maybe 10 or 20 times the mass of our sun. Over billions of years, this seed feeds. It eats gas, it eats dust, it merges with other black holes. Slowly, patiently, it grows into the giants we see today, millions or billions of times the mass of the sun. This growth takes time. It is a slow meal. Nature has a speed limit for how fast a black hole can eat. We call this the Eddington limit. Imagine a fountain. If you pour water into a cup, you can only pour so fast. If you pour too quickly, the water splashes out, the cup pushes back. It is the same with a black hole. As matter falls in, it heats up, it glows, it releases radiation. That radiation pushes outward against the infalling gas. If the black hole tries to eat too much, too fast, the burp of radiation blows the food away. It starves itself by being too greedy. So, under the laws of physics as we know them, A baby black hole born shortly after the Big Bang should not be able to grow very large in just a few 100 million years. It simply cannot swallow enough matter without choking. But the James Webb Telescope has found something that defies this limit. Deep in the data, looking back to when the universe was less than 500 million years old, Webb found a quasar. A quasar is a black hole that is feeding so furiously it outshines its entire galaxy. The object is known as UHZ-1. When astronomers measured the mass of this black hole, they were stunned. It was not a seed, it was a titan. It was millions of times the mass of our Sun. It was nearly as heavy as the entire galaxy surrounding it. In the modern universe, the black hole is usually a tiny fraction of the galaxy's mass, a grapeseed inside a pumpkin. But in the early universe, Webb is seeing pumpkins where the seed is the size of a melon. The ratio is wrong, the balance is broken. How did this monster get so big so fast? If it started as a star, it would have had to eat constantly, at the absolute maximum speed limit, without pausing for a single second, for hundreds of millions of years. And even then, the math barely works. It is like finding a giant redwood tree in a garden that was planted yesterday. This discovery adds a terrifying layer to the pattern. It suggests that the early universe was not just making stars too fast, it was making monsters too fast. This leads us to a theory that was once considered fringe, a whisper in the halls of academia, but is now being spoken aloud. It is the theory of heavy seeds. Perhaps the first black holes did not come from stars at all. Imagine the early universe again. The gas is hot, dense, and thick. In our standard story, this gas cools down, fragments into small clumps, and makes stars. But what if, in some places, the gas did not fragment? What if a massive cloud of primordial hydrogen, thousands of light years across, suddenly collapsed under its own weight? It would not make a star. It would be too big. Instead, it would skip the star phase entirely. It would collapse directly into the dark. This is called direct collapse. A cloud of gas, heavy with the potential of 1,000,000 suns, falling inward, crushing itself into a singularity in a single moment. If this happened, the seed would not be small. It would be born huge. It would be a heavy seed, tens of thousands of times the mass of the Sun right from birth. It would start the race with a massive head start. The pattern Webb is seeing, these impossible galaxies with their impossible black holes, might be the evidence of this violent beginning. It paints a picture of the cosmic dawn that is far more dramatic than we thought. It was not a slow awakening. It was a time of cataclysm. Giant clouds vanishing into darkness, birthing monsters that immediately began to shape the galaxies around them. The black hole, in this new story, is not the result of the galaxy. It is the anchor. It is the architect. Let us visualize this. In the deep infrared dark, a direct collapse black hole forms. Its gravity is immense. It pulls in streams of cold gas from the cosmic web. This gas swirls around the black hole, heating up, glowing with the energy of 1 billion stars. This heat pushes outward, compressing the surrounding gas clouds, triggering a shockwave of star formation. So, the galaxy grows because of the monster in its middle. This reverses our logic. We used to think galaxies formed, and then black holes grew in the quiet centers. Now, the pattern suggests the black hole came first, or at least arrived at the party at the same time, hungry and commanding. The James Webb Telescope is showing us a universe where the dark ages were punctuated by these intense beacons of consumption. It is a universe that was in a hurry. Why was it in a hurry? What drove this rapid assembly? This brings us to the edge of the map. If the black holes are too big and the galaxies are too bright, we have to look at the invisible scaffold that holds it all together. We have to talk about the ghost in the room. We have to talk about dark matter. Standard cosmology assumes dark matter is cold. This means it moves slowly. It clumps together gradually. It takes its time to build the halos that trap the gas. But the pattern Webb has detected, this pattern of early maturity, might be whispering that dark matter is not what we think it is. Maybe it isn't cold. Maybe it is fuzzy. Maybe it interacts with itself. Maybe in the early universe the rules of gravity were slightly different. We are looking at the data, and the data is uncomfortable. It does not fit the curve. And in science, discomfort is the most exciting feeling of all. Discomfort means we are about to learn something new. The silent eye of the telescope has found the giants. It has found the monsters. And now, it is forcing us to rewrite the history of the dark. As we float here, suspended in the stillness between the galaxies, let us allow ourselves to speculate. Let us allow the mind to wander into the realm of the theoretical. The data from James Webb is a series of dots on a graph, but the line connecting those dots is a story. And right now, the line is broken. To fix the line, to explain the pattern of the impossible early universe, physicists are beginning to dust off old books and write new equations. The silence of the cosmos is being filled with the whispers of a new physics. One of the most intriguing whispers concerns the very beginning of time itself. We speak often of the Big Bang as a singular event, an explosion of space and time. We assume that after the bang, the universe was smooth, a perfect, expanding fluid. But what if the bang was not smooth? What if the birth of the universe was messy? There is a theory known as primordial black holes. It suggests that in the fraction of a second after the universe began, long before atoms formed, long before light could travel, the density of the universe fluctuated wildly. In some tiny pockets of space, the energy was so dense that it simply collapsed. These pockets would become black holes. Not from stars, not from gas clouds, but from the pure, raw energy of the Big Bang itself. If this theory is true, then the universe was born sprinkled with these black holes. They would be everywhere. Tiny ones, massive ones, silent seeds scattered through the cosmos before the first second of time had ticked by. If these primordial black holes existed, they would solve the mystery Webb has uncovered. They would act as the seeds for the galaxies. They would be the magnets already in place, waiting for the gas to cool. The gas would not need to wait for gravity to slowly build a trap. The trap would already be there. The gas would fall into these primordial wells, piling up, igniting into stars, and creating the massive bright galaxies we see in the deep fields. It would explain why everything looks so mature. The structure didn't have to evolve, it was baked into the bread. It is a beautiful, elegant idea. But it is also terrifying. It implies that the universe is filled with these ancient, invisible remnants of creation, hiding in the halos of galaxies, perhaps even floating through our own solar system. But there are other whispers, other theories that are even more radical. Some scientists are looking at the pattern and asking, is our clock wrong? We measure the age of the universe by the rate of its expansion. We look at how fast the galaxies are moving away from us, and we rewind the tape. This gives us the number 13, 8 billion years. But what if the expansion hasn't always been the same? What if, in the very early universe, there was a strange form of energy, an early dark energy, that flared up and then vanished? This pulse of energy would have changed the way the universe expanded in its first moments. It would mess with our ruler. It would mess with our clock. If we account for this early dark energy, it might shift the timeline. It might mean the universe is effectively older than we think, or that processes happen faster because of this extra push. It is like discovering that a runner who broke a world record had a strong wind at their back that no one noticed. The result is the same. The record is broken, but the cause is invisible. And then, there is the most profound whisper of all, the one that challenges the most famous name in physics, Einstein. Our understanding of gravity comes from general relativity. It is a perfect theory. It works for the orbits of planets. It works for the bending of light. But we have never tested it on the scale of the infant universe. There is a school of thought called Modified Newtonian dynamics. It suggests that on the scale of galaxies, gravity behaves differently. It suggests that we don't need dark matter at all. If gravity is stronger in the weak acceleration of deep space, then gas would collapse faster. Stars would form easier. Galaxies would assemble without the need for massive halos of invisible matter. If Mund is right, then the James Webb Telescope is seeing the impossible galaxies because our rulebook for gravity is missing a page. It would mean that the universe is not filled with dark matter, but is simply governed by a gravity that hugs it tighter than we realized. We do not know which of these whispers is the truth. Perhaps it is none of them. Perhaps it is a combination. But let us pause and appreciate the moment we are in. For decades, cosmology was becoming boring. We thought we had it solved. We had the standard model. We had the percentages: 68% dark energy, 27% dark matter, 5% normal matter. It was a neat, tidy pie chart. The James Webb Telescope has taken that pie chart and thrown it into the air. It has given us a gift, the gift of ignorance. We are learning how much we do not know. The pattern no one can explain is a door. We have walked through it, expecting to find a dusty attic, and instead, we found a cathedral. The pillars of this cathedral are made of ancient light. The floor is made of heavy seeds, and the ceiling is lost in the darkness of a time before stars. As we examine the spectrum of these distant galaxies, we see other strange things. We see Pot 3 stars, or rather, the lack of them. Population 3 stars are the theoretical first generation. They should be made of pure hydrogen and helium, no metals, no dust. They should be the holy grail of astronomy. Webb was built to find them, but so far in these massive early galaxies we see carbon, we see oxygen, we see neon. The universe got dirty, with elements remarkably fast. This chemical richness connects to us. The carbon in these early galaxies is the same carbon that makes up the organic molecules of life. If the universe was creating these elements in abundance just 300 million years after the Big Bang, then the ingredients for life were present almost from the start. We used to think the early universe was a hostile, sterile place, a place of radiation and raw gas. But the pattern suggests it was a fertile place, a place where the chemical complexity of life was being cooked up in massive, bright kitchens at the edge of time. Could it be that the universe is biocentric? Could it be that the rush to form galaxies, the rush to create heavy elements, is a fundamental drive of the cosmos to create observers? That is a philosophical question, not a scientific one. But as we float here, watching the data stream in, the line between physics and philosophy begins to blur. We are seeing a cosmos that is eager to build, eager to shine, eager to wake up. The pattern is undeniable. The red jewels are there, the heavy black holes are there, the chemicals are there, the timeline is strained, the models are cracking, and in the silence of the observatory, the scientists are smiling, because a broken model is the only way to build a better one. We are standing on the precipice of a revolution in how we understand our origins. The silent eye continues to stare. It captures another photon, another piece of the puzzle. And as it does, the universe feels a little larger, a little stranger, and infinitely more beautiful. Let us drift one final time into the deep field. We have spoken of the silent eye, the broken timeline, and the heavy seeds. Now, we must speak of the environment. We must look at where these impossible galaxies live. In the standard model of cosmology, the early universe was a lonely place. Galaxies were islands in a vast, expanding sea of dark matter. They were supposed to be rare, isolated, and disconnected. But the James Webb Telescope has revealed something else. It has revealed a web. When we look at the placement of these massive early galaxies, we see that they are not scattered randomly like poppy seeds on a bagel. They are clustered. They are huddled together in groups. This is the cosmic web. It is the largest structure in the universe, a vast network of filaments made of dark matter and gas, stretching across billions of light years. The galaxies are the pearls strung along these invisible threads. We knew the web existed in the modern universe. We can see it in the distribution of galaxies today. But we did not expect to see it so clearly, so early. The Webb telescope has found protoclusters. These are groups of galaxies in the process of merging. But in the deep past, at a redshift of 7 or 8, when the universe was less than 800 million years old, these protoclusters are already massive. Imagine a city under construction. You expect to see scattered foundations, a few cranes, maybe some roads being laid, but what Webb is seeing is a skyline. It is seeing high-rises already topped out. It is seeing traffic flowing between them. One specific example is a protocluster named A2744Z70D. It contains at least 7 galaxies. They are all bright. They are all forming stars at a furious rate. And they are all packed into a volume of space that is incredibly small. If you stood on a planet inside one of those galaxies, the night sky would be dazzling. You would see the other 6 galaxies not as faint smudges, but as huge, swirling nebulas dominating the darkness. It would be a crowded, brilliant sky. This crowding tells us that the universe was organized very quickly. Gravity didn't just pull gas into galaxies, it pulled galaxies into neighborhoods. It created community. And within these neighborhoods, the interactions are violent. Galaxies in the early universe are not polite. They collide, they merge, they tear each other apart. This is the dance of the giants. When 2 gas-rich galaxies collide, the gas clouds slam into each other. This triggers a shock wave of star formation. It is a starburst. The entire galaxy lights up with new, hot blue stars. The James Webb data shows us that this dance was happening everywhere. It was a chaotic ballroom. The universe was a place of constant mergers. But here is the mystery. Mergers take time. For 2 galaxies to find each other, fall into each other's gravity orbit and then merge takes hundreds of millions of years. It is a slow waltz. If we are seeing massive, merged galaxies at the dawn of time, it means the waltz must have started the moment the music began. It means the galaxies formed incredibly close to each other. This reinforces the idea of peaks in the density of the early universe. It suggests that the primordial fluctuations, the ripples in the fabric of space-time from the Big Bang, were much sharper than we thought. Think of a mountain range. If the peaks are high and close together, the valleys are deep and narrow. The water gas flows quickly into these valleys, creating deep lakes, galaxies that are right next to each other. If the peaks were low and gentle, the water would spread out. The lakes would be shallow and far apart. The standard model predicted low, gentle hills. Webb is showing us the Himalayas. This topography of the early universe changes everything. It means that the conditions for galaxy formation were not uniform. They were extreme. There were hotspots of creation. And inside these hotspots, the environment was intense. The radiation from all these young stars and feeding black holes would have been fierce. It would have ionized the gas around them. This brings us to the epoch of reionization. After the Big Bang, the universe was filled with neutral hydrogen. It was a fog. Light could not travel freely. Then the first stars turned on. Their ultraviolet light smashed into the hydrogen atoms, stripping away their electrons and turning the fog into transparent plasma. We used to think this process took 1 billion years. We thought it was a slow burn, like morning mist clearing over a lake. But the pattern of bright, clustered galaxies suggests that reionization might have been patchy and fast. In these dense neighborhoods, the fog would have cleared almost instantly, creating bubbles of clear space. These bubbles grew and merged until the entire universe was transparent. We are looking at the bubbles. We are looking at the holes punched in the dark by the first giants. The telescope has also found something unexpected in the chemistry of these clusters. We see PAAHs, polycyclic aromatic hydrocarbons. These are complex organic molecules. They are found in smoke, in soot, and in the dust between stars. Finding PAHs this early is like finding complex sentences in a baby's first babble. It implies a level of chemical sophistication that should require billions of years of stellar processing. It suggests that the universe is a chemical factory that ramps up to full production almost immediately. As we float here, observing the dance, we must appreciate the sheer scale of what we are witnessing. We are seeing the assembly of the structure of reality. We are seeing the bones of the universe being knit together. The pattern no one can explain is the pattern of life itself. It is the pattern of complexity emerging from simplicity. It is the pattern of light conquering the dark. And it is happening faster, brighter, and more efficiently than we ever dared to dream. We have journeyed far. We have traveled from the silent, cold mirrors of the James Webb Space Telescope to the roaring hearts of ancient quasars. We have seen galaxies that are too big, black holes that are too heavy, and a cosmic web that is too intricate for its age. We have faced the discomfort of the unknown. We have seen our standard model of cosmology shaken, if not broken. But in this final reflection, let us move beyond the data. Let us move beyond the redshift and the spectra. Let us ask, what does this mean for us? We are the children of this universe. We are made of its dust. The iron in our blood was forged in the hearts of stars that died billions of years ago. The oxygen we breathe was created in the fusion reactors of ancient suns. If the universe was born mature, if it was born with a capacity for complexity that was immediate and profound, then perhaps we are not an accident. For a long time, science has told us a story of loneliness. It told us that we are a fluke, a lucky roll of the dice in a cold, indifferent, and empty cosmos. It told us that life is a rare, fragile scum on a rock, existing in a universe that took eons to become habitable. But the pattern Webb has found tells a different story. It tells a story of a universe that was ready for life almost from the beginning. A universe that rushed to create the heavy elements, the carbon, the nitrogen, the oxygen needed for biology. A universe that built massive, stable galaxies to house solar systems when time itself was just getting started. If the ingredients for life were present 13 billion years ago, then life might not be a latecomer to the party. We might be the latest in a long, long line of observers. Imagine civilizations rising and falling in those bright, red galaxies at the dawn of time. Imagine eyes looking up at a sky filled with young blue stars, wondering about their origins just as we do. The pattern no one can explain suggests that the universe is not a barren desert, but a garden. A garden that blooms quickly, a garden that is desperate to produce flowers. The James Webb Space Telescope is our way of walking back into that garden. It is our way of meeting our ancestors. We built this machine out of curiosity. We built it because we wanted to know where we came from. We expected to find a simple answer. We expected to find a slow, gradual path. Instead, we found a mystery. We found a universe that defies our expectations. A universe that is wilder, stranger, and more powerful than we could have imagined. This is the beauty of science. It is not about being right. It is about being wrong and then looking closer. The pattern is an invitation. It invites us to think bigger. It invites us to let go of our rigid models and embrace the fluidity of the cosmos. Perhaps gravity is different. Perhaps dark matter is different. Perhaps the Big Bang was different. It doesn't matter. What matters is that we are here to see it. What matters is that we, a small species on a small planet, have built an eye capable of looking back to the beginning of time. As the telescope continues its silent vigil, orbiting the Sun 1 million miles from Earth, it will send back more data. It will find more anomalies. It will break more rules. And with every broken rule, we get closer to the truth. We are not at the end of the story. We are at the beginning of a new chapter. The universe has just opened its diary, and we have only read the first page. The pattern is there. It is waiting. The galaxies are glowing in the infrared dark. The black holes are humming. The cosmic web is stretching across the void. And somewhere in the data is the key. Let us keep looking. Let us keep wondering. Let us keep drifting through this beautiful, impossible ancient dark. For in the end, the pattern is not just about the stars. It is about us. It is about our ability to see, to understand, and to marvel at the grand, silent majesty of the universe. The eye is open. The silence is speaking. and we are listening. We have spoken of the galaxies that are too big and the black holes that are too heavy. But there is a third ghost haunting the data. It is a ghost that lives in the mathematics of the universe itself. It is a conflict known as the Hubble tension. To understand this tension, we must imagine the universe as a balloon being inflated. We want to know how fast the skin of the balloon is stretching. This speed is called the Hubble constant. For years, we have had two ways to measure this speed. The first way is to look at the baby picture of the universe, the cosmic microwave background. This is the faint glow left over from the Big Bang. By measuring the ripples in this glow and using our standard model of how the universe grows, we can predict how fast the universe should be expanding today. The answer comes out to be 67 kilometers per second per megaparsec. The second way is to look at the adult universe. We look at pulsating stars called Cepheids and exploding stars called supernovae in nearby galaxies. We use them as mile markers. We measure their distance and their speed directly. When we do this, we get a different number. We get 73 kilometers per second per megaparsec, 67 and 73. These numbers are not the same. The difference may seem small, but in the precision world of astrophysics, it is a chasm. It is a screaming contradiction. It means that the universe is expanding faster than it should be, based on its initial conditions. Before the James Webb Telescope, there was a hope. The hope was that perhaps we were just measuring it wrong. Perhaps the Hubble Space Telescope with its older eyes was making mistakes in measuring the brightness of the Cepheid stars. Perhaps the dust was getting in the way. We hoped that when Webb opened its golden eye, it would look at those Cepheids with perfect clarity. We hoped it would refine the data and bring the number 73 down to 67. We hoped it would heal the rift and save the standard model. But Webb did not heal the rift, it deepened it. Webb looked at the Cepheids with infrared vision that cut through the dust. It separated the light of the stars from the background clutter, and it confirmed the measurements. The number 73 is real. The local universe really is expanding faster than the laws of physics say it should. This connects back to our pattern no one can explain. If the universe is expanding faster now than we predicted, and if galaxies formed faster in the past than we predicted, we are seeing the symptoms of a single underlying condition. The universe is more energetic, more dynamic, and more aggressive than our textbooks allow. Something is pushing the accelerator. This brings us back to the concept of early dark energy. Imagine the universe in its first moments. We know it was dominated by radiation. But what if there was a fleeting, intense field of energy that existed for only a brief epoch, perhaps just 100,000 years after the Big Bang, and then decayed? This energy would have given the universe a kick. It would have fundamentally altered the size of the sound waves traveling through the primordial plasma. It would change the calibration of our ruler. If this kick happened, it would explain why the universe looks older and more evolved than it is. It would explain why the Hubble constant is broken. It would explain the mature galaxies. It suggests that the history of the cosmos is not a smooth curve. It is jagged. It is punctuated by events we have not yet named. The crisis of the constant is not a failure of science. It is the sound of a door unlocking. It tells us that there is a missing ingredient in our recipe for reality. We are like map makers who have discovered an island that shouldn't be there. We can ignore the island and stick to the map, or we can throw away the map and start sailing toward the unknown shore. Webb has forced us to sail. And as we sail, we realize that this crisis affects everything. It affects the age of the universe. If the expansion is faster, the universe might be younger than 8 billion years. But if the galaxies are mature, they need to be older. Do you see the paradox? We have a universe that looks incredibly old yet might be incredibly young. This paradox is the fertile ground where the next Einstein will grow. It is the soil of revolution. We are living in the most exciting time in cosmology since the 1920s. The silence of the deep field is deceptive. Behind the silence, the equations are burning. Let us turn our gaze from the edge of time to something closer. Let us turn from the giants of the past to the neighbors of the present. The pattern no one can explain is a pattern of early maturity. It is a pattern of heavy elements, carbon, oxygen, nitrogen, appearing almost instantly in the cosmic story. If the universe was rich with these elements 13 billion years ago, then it implies that planets, rocky, watery, chemically complex planets, have been forming for a very long time. The James Webb Telescope has a second mission. It is not just a time machine, it is a chemist. It is a sniffer of atmospheres. In the darkness of our own galaxy, there are stars that are not like our Sun. They are small, cool, and red. These are M dwarfs. They are the most common stars in the universe, and orbiting these stars are rocky worlds. One such system is TRAPPIST-1. It is a mere 40 light-years away. It has 7 Earth-sized planets packed tight around a dim red star. 3 of them are in the habitable zone, where water can exist as a liquid. Webb has been staring at these worlds. It waits for the planet to pass in front of the star. As the planet passes, a tiny fraction of the starlight filters through the planet's atmosphere. The gases in the air absorb specific colors of that light. By analyzing the missing colors, Webb can taste the air of an alien world. This is the most delicate measurement ever attempted. It is like trying to see a firefly hovering next to a searchlight from 1,000 miles away, and then trying to tell what color the firefly's wings are. The early data from TRAPPIST-1b, the innermost planet, was stark. It showed no thick atmosphere. It was a bare rock scorched by its sun. But the search continues for the outer planets. We are looking for carbon dioxide. We are looking for methane. We are looking for water vapor. And, in our wildest dreams, we are looking for the combination of gases that does not belong. Oxygen and methane. On Earth, these two gases destroy each other. They react and vanish. The only reason they both exist in our atmosphere is that life, bacteria, plants, animals, is constantly pumping them out. If life stopped on Earth, the oxygen and methane would react and disappear. Finding these two together on another world would be the biosignature. It would be the smoking gun of life. Now, connect this back to the deep field. Connect this back to the impossible galaxies. If the universe created the conditions for life 13 billion years ago, then life has had 13 billion years to evolve. It has had 13 billion years to spread. We have always assumed that we are early. We assume we are the first to wake up. But the pattern of the early galaxies suggests we might be late. Imagine a civilization that arose in one of those impossible bright red galaxies at the dawn of time. Their star would have burned out billions of years ago. Their galaxy would have merged, changed, and evolved. They would be the ancients of the ancients. If the universe is biased toward complexity, as the Webb data implies, then the silence of the sky becomes even more profound. This is the Fermi paradox. If the universe is so efficient at building galaxies, stars, and planets, then where is everyone? Perhaps the answer lies in the nature of time itself. Maybe civilizations are like the POP3 stars, bright, intense, and short-lived. Maybe the universe is a garden that blooms in waves. Or perhaps we are simply looking for the wrong thing. We are looking for radio signals. We are looking for structures. But maybe a civilization that is billions of years old does not build with metal and stone. Maybe they build with gravity. Maybe they live in the dark matter. The James Webb Telescope cannot see aliens, but it can see the potential for them. It is showing us that the house of the universe was built quickly, furnished with the heavy elements of life, and has been standing ready for occupants for eons. It forces us to feel a deep, abiding humility. We look at the TRAPPIST system, and we see our own potential future. We look at the deep field, and we see our ancient past. The line between the two is unbroken. The carbon in your hand is the same carbon that glowed in Jade's JWST. The oxygen in your lungs is the same oxygen that Webb is hunting for in the atmosphere of K218b. We are not separate from the anomaly. We are the anomaly. We are the universe realizing it is awake. As the telescope drifts through the cold vacuum, cooling its mirrors, pointing its guidance sensors, it is doing the most human thing possible. It is asking, why? And the universe, in its vast, silent, glittering language, is beginning to answer. So, where do we go from here? The story of the James Webb Space Telescope is far from over. It has a fuel supply that could last for 20 years. It has thousands of hours of observation time yet to be allocated. There are still blank spots on the map. One of the next great frontiers is the cosmic dark ages proper. We want to see further back than even the first galaxies. We want to see the hydrogen fog before the lights turned on. Webb will attempt to do this by looking for the 21-centimeter line, a faint radio signal emitted by neutral hydrogen. Mapping this signal would give us a 3D map of the universe before structure began. It would show us the seeds of the seeds. It will also turn its eyes closer to home. It will look at the ice giants Uranus and Neptune to understand how our own solar system formed. It will look at the moons of Jupiter and Saturn, specifically Europa and Enceladus, where oceans of liquid water lie hidden beneath miles of ice. Could there be life there, in the dark, warm oceans of our own solar neighborhood? Webb might see the plumes of water venting into space, tasting them for the salt of life. And beyond Webb. We are already dreaming of the next machine, the Habitable Worlds Observatory, a telescope designed specifically to image Earth-like planets. A machine that will not just taste the atmosphere, but map the continents. But for now, we have the golden eye. We have the pattern no one can explain. And perhaps we should be grateful that we cannot explain it yet. A mystery solved is a fact filed away. A mystery unsolved is a living thing. It drives us. It keeps us awake at night. It makes us build rockets and mirrors and sensors. The confusion is the fuel. The universe is telling us that our imagination was too small. We imagined a slow, boring, lonely start to the cosmos. The universe has corrected us. It has shown us a start that was fiery, crowded, rapid, and magnificent. It has shown us that the dark is not empty. As we end this journey, let us hold two thoughts in our minds. First, the vastness, the sheer, crushing scale of the distance. The light from those red galaxies has traveled for so long that the Earth did not exist when it started its journey. Second, the intimacy. The fact that we, tiny creatures of carbon and water, have managed to catch that light. We have built a bucket to catch the rain of history. We are the universe's way of knowing itself. And right now, the universe is surprising itself. The pattern is there. The silence is broken. And the story continues.